thank you again. It's a really a good privilege to come here on behalf of John and to see everybody again. I will be talking about Quicycle, a very quick introduction about the group, who we are, what we do, and talking through some of the tools that we have developed in the group, mainly focusing on the computational tools, which is kind of something that I'm familiar with, that I have created as well. And then toward the end of the talk, I'll also give a brief introduction to what a SiMART is. Okay. So I'm a big proponent of the what you see is what you get. So this is how the about page in the Quicycle website looks like, and this is hence what you get in my presentation. So as you can see, the Quicycle group was co-founded by Dr. John Williamson and his friend Dr. Martin and Mark. We are basically a think tank, and we basically as a group want to further pure science, enable thinking, which is not generally the standard thinking, so things like thinking about out-of-the-box stuff, for example, things beyond the standard model, and also talk about things like excluding the untested. So it's good to have a theory, but it's just a theory, and the final arbiter is usually experiment. So if the theory or the model does not stand with the correctness of the experimental data, we have to be bold and apply the scientific method, which is to think better and learn from our mistakes. So these are some of the things that we basically stand for in the group. One of the things that we also want to do in our group is basically disseminate knowledge that we have acquired from the different people who have worked with us. And part of this is basically as a journal section in our website, where we try to put different papers that we have been working on, and we also try to have like a peer review system, so that basically we can have like how much the paper has been tested and reviewed by people and something like that. There's also a lot of work done by Arnie, who has been involved in looking at the chemical properties of matter, which comes from the subquantum theory, which basically John and Martin were working on, which probably some of you would be already familiar with, which is basically they say that the electron can be seen as a double loop rotated photon, and how the properties like charge and mass of the electron emerge. So Arnie has been working on the chemical aspects of that. Then we also have Dr. Vivian Robinson, who has been working on things like gravity. So there's a lot of material over there. I would highly encourage to have a look and see what may trigger your interest. Okay. Next, there's the computational tools section in the website, and this is exactly what you see there as well, and what you get in my presentation. So you've got three items at the moment. So one is the AR algebra, the absolute relativistic algebra, which I will very briefly touch upon. I'm not the best guy to talk on this. There's another guy, Ines Morrison, who has been working on this, and I'll briefly touch on that. Then there's the physics modeling part, which is basically the icon of the picture. So there is a set of tools that I've developed. It's open source software, which I'll be talking about, which can be used for solving 2D physics problems. What kind of problems and how exactly the solution will work, I'll be talking more about it in the presentation. And then finally, the subquantum modeling is a space that you can be watchful for. So this is something that we are working on, and SiMART is basically the product that is going to encompass that. Okay, so what's the AR algebra, the absolute realistic algebra? So well, it's a statistical algebra, and that is used by John and Martin's work. So from an outsider, the way I see it is like this. So the algebra is such that it defines anything that is physical, does not come without its proper unit. So for example, if you have a distance in the z direction, then you have the magnitude z and the unit k. The other thing about the algebra is that every unit has some three different properties. One of the things that is of interest to me is how do these units square? So for example, the unit k would square to a plus 1, for example, and then it will give you a metric. Okay, how does a metric for space and time work? For example, Garnier was talking about earlier, right? The Minkowski's space metric and so on like that. So mind you, in this representation here, like where I say that k squared equals plus 1 and p, is because plus 1 is the magnitude and p is the unit. And in the algebra, even the scalars have a unit, which means the unit of the pixel, for example. So yeah, everything has a unit, and the units have three properties. There are, in a sense, a total of 16 units. So the way I see it is like you've got 3 space and 1 time. So there are 4 different units which basically can be or not be in a minute to make a unit. So it's like 2 to the power 4, which is 16 different units that you can have. And they are symboled as alpha 0 all the way up to alpha 15 should be to number 60. It's my bad. And here is a multiplication table for all these elements. So what happens if you multiply alpha 0 with alpha 1, alpha 0 with alpha 0, and so like that. So imagine on the top column you have all these different alphas, and on the left rows basically you have the other alphas. So the matrix that you get is a general multiplication matrix, and this is also another work that was done by Ines. And he color codes these elements of the matrix to have some sort of pattern behind it. So I'm not the best person to talk about this. Perhaps it would be a good idea to upload one of these talks on our website, which is hopefully will become soon. So yeah, these multiplication tables tell us how, if we have different units, how they should be expanded on something. So the work that Ines has done is basically like a symbolic operator. It basically tries to look at the different operations of units. For example, if you're differentiating a unit with another unit, if you're multiplying different units, how you should be expanding, and what are the other units that you would be getting out of such an operation. So he has used this to basically proof check different expressions that John and Martin were using in the past. So it has proved to be quite useful. Now we go on to things which are more familiar to me, which is physics modeling. So here you see basically, well, I have a GitHub page, and what it provides is basically an open source software written in Fortran, which allows you to solve different kinds of physics problems. This is just an example. So on the left, you see a grid, basically 2D grid, which has been discretized, over which we are solving a simple wave problem. So there is a source inside this domain, and we're trying to solve this certain sort of boundary conditions. So yeah, it can be used to solve different kind of initial problems. These are the links for the 3 colors that the software comes into. So I call them LSM, PALFM, and HiFM. Why and what do they do? I'll be talking more about it in the coming slides. Okay, so just very quickly, this is the flowchart of the code. Probably not many of you would be appreciating this, but this is very interesting to me because it dissects the code into 2 main blocks, with a middle block which is colored in blue over here. So the upper block basically talks about how to implement the initial values, like what are the initial values of the physical problem, like what is exactly at the boundary, if it is a time-dependent problem, what is happening at time 0 and stuff like that. And the later part, the part after the blue grid, is basically where if you have a time-dependent system, it tries to evolve the solution over time, basically. And the blue bit basically tells you how to configure your solver, like what is the order of accuracy that you want to have, what different kinds of integration schemes you want to use and stuff like that. So that's basically the flow chart of the code. It does not really have a graphical user interface. It's more like you have a configuration file that you can sort of modify to your heart's content, and you can play with it. But the good thing is that it works, and it has been tested for different problems as well. Okay, so whenever I talk about my model, I always try to start with the Laplacian, which I believe is probably the best thing we did as humans to learn how to solve the Laplacian. Because in my opinion, Laplacian, when you solve them, they give rise to these functions which are called the harmonic functions. And also it gives me a very nice way to introduce to the 3 different families of partial differential equations, and hence the name that I got showing for the solver. So if you look at just the homogeneous Laplace equation and its variance, basically it's just a second order spatial derivative operator, right? So that basically gives us a family of what is known as an elliptic partial differential equations. And these equations can be used to model systems which are in their steady state. So for example, if you have, let's say, a steady stable electric field and you want to look at the distribution of the potential gradient, so that's a very steady state system, right? Like, and it's not changing much with time. So you can use elliptic family to basically model such a system. Then you've got, if you add just one time derivative, the first order time derivative to the system, basically it becomes what is known as a parabolic system. This family can be used to model systems which basically look like some sort of diffusion, where some sort of mixing is going on. So example could be heat convection, heat diffusion, and that kind of stuff. Then if you add a second order derivative of time to the Laplacian, it becomes a parabolic system. And this hyperbolic system, and this family can be used to solve transient and oscillatory behavior of systems. For example, if you drop a pebble in a very silent pond, or if you want to look at how acoustic waves travel in a room, for example, or even light waves, for example. So these wavy and transient behaviors can look very nicely using these hyperbolic modes. And hence we get the name, elephant, parafem, and hyphen. Now you go to the first bit, understood the first bit. The fem is basically really the method that I'm using, so finite element modeling. And I'll basically be doing very brief introduction to what finite element is and how it basically contrasts with its another counterpart, which is used very widely as well, which is the finite differences. Okay, so the SiMART, what in the SiMART project, what we want to do is we want to combine the power of the finite element modeling with the power of AR algebra. There is a graph on the right-hand side which I would like to keep as a mystery for now, and I'll come back to it toward the end of the talk. Okay, so now I give a very brief introduction of different literature review kind of for different numerical methods. So as you may know, the finite differences, it's very widely used and it's very easy to implement. It's literally just a matter of very quick coding that we can implement a finite difference technique. One of the big drawbacks of using finite differences is that it can not be easily applied if you have a complex geometry problem. For example, if you have something very rectangular, very cubic, it's fine. They love to solve things which are very nice, square. But if you have something which is got more curves, more interesting features, then you basically have to succumb to very fine meshes or very fine discretization of the geometry, which essentially increases the computational cost, like how much you take time to solve. Finite elements on the other side is also widely used, but it can deal very easily with the complex geometry. And the good thing, which I personally like about finite elements, it basically gives you a solution in a functional space, which is more controlled, in my opinion, than what you get for finite difference schemes. One of the problems with finite elements is the boundary truncation. So what I mean by that is, let's say if you want to model an antenna of a mobile phone, then you can have geometry for that. But then you want to ask the question, what is the boundary until which you want to compute your physical solution, numerical solution, basically. So the general rule of thumb is you want to include a big enough area or volume around your geometry so that all these perturbances really die out and they don't really reflect back from the boundaries as a numerical artifact or something like that. So hence, if you're really looking at really bigger problems, then a lot of the geometry really is only to have a big enough volume around your geometry of interest, which is not a good feature, but otherwise it's a really good and interesting method. Then we also have boundary elements, in which you actually solve the problem only on the boundary, so you don't really worry about what inside the boundary, and you can just interpolate or extrapolate your results inside. So basically it reduces the problem of how you truncate the boundary. You literally just solve at the boundary. The problem here is it's only useful if you have a low surface to volume ratio. So what I mean by that is that the boundary should be smooth enough. So if you have a lot of zigzags or whatever, which increases the surface area, this ratio does not really become very well, and the boundary element is not very good for that. It is very useful for looking at contact problems. So for example, things like if there are objects which are colliding with each other, how they deform, and even for crack propagation and stuff like that. So this was just a very quick show of what I did in PhD for literature review. There are all different methods that you can think of, like fine volumes, the algebraic topology, the Ritz method, and so on like that. But as my supervisor would have said, there is not one panacea method of solve everyone like we all would want to have. They all come with advantages and disadvantages. Okay, next I give you a very quick overview of what a finite difference is. So generally speaking, in finite differences, what we do is we approximate a differential equation with a difference equation. So you may see that a differential operator, for example, the dx of a function f of x, can be seen as as a limiting case of a ratio between the increment of the function as the increment of the x changes, for example, right? In 1D, for example, if you think of it, it generally requires using a stencil, so at least 2 points where you want to compute the increments, and then also deciding where exactly your slope or the ratio is going to be situated at. So that gives you different stencils and also different flavors of this method, which can be seen as explicit or implicit for different kind of stability conditions. So you may have heard of backward order or forward order. These are just simple examples of how many points that you use for discretizing the grid and calculating the slope, for example. So essentially, the one key takeaway from this slide is basically that in finite differences, you really approximate the derivative with a difference ratio. These are supposed to be some examples. Let me see if they work. Okay, yeah. In the top half of the slide, you can see it's an example of an acoustic wave. But what I try to do is simulate something very similar to a Young's double slit. It's literally just an acoustic wave trying to hit a slit with 2 holes, and the boundaries are affected, so it basically comes back. On the bottom image, basically we have a 3D version of the code where you want to solve, let's say, a line distribution of charge, and it's oscillating along the z-axis, and how it basically disturbs the electric and magnetic field around it. So these codes were done in MATLAB, and as you can see, it's easy to work on things which are very simple, which are very rectangular and cubic. But the more complex geometry you want to get, the more fine meshes you'll have to use, and it becomes a bit more costly. So these are the examples for the fine difference and content studies. Now, what happens when you go to finite element method? So imagine if your solution is f of x. So instead of looking at the derivative, what we do in finite element is basically we look at approximating the function in a very nice basis. So what I mean by that, let's say your function f of x is say kx plus bx squared plus cx cubed. Then you say that, okay, let's say we have a 3-dimensional basis of an x-axis, an x squared axis, and an x cube axis. Then the function literally is just a point in that space with the coefficients a, b, and c. So that's the key idea behind finite elements, in which you want to approximate your solution in a space which is formed by some sort of functional functions as the basis. So hence the function space in which you want to approximate your solution. This is an example of a 1D polynomial basis in which you can have either first order approximation in which you just have linear interpolation between different points, or you can have second order polynomials in which you have kind of like parabolic interpolations for different points. Similarly, you can have examples of 2D elements in which you have these different shapes, and what you're saying is how much of each shape is contained in my actual solution. So it's like tuning different shapes and seeing which one has the most energy, basically our information contributing to our solution. So if you think of it in terms of Fourier transforms, you can say if you have, let's say, a song, what is the Fourier transform? Basically tells you what are the frequencies which are most prominent, and each frequency has a component. Similarly, in a finite element function basis, we're looking at different shape functions, and you're asking the question how much of these element shape functions are inside your actual solution at 2D. Here are some other examples of what a function space can be in 1D. So on top you have, let's say if you have a digital signal and you want to sample it, the way to do it is by using the Dirac delta functions as a basis. We just use spikes to sample the signal at different time points in time, and it becomes like a array of different Dirac delta functions sampled at different time steps. In the second example, you see a polynomial basis in which you have your function as a series sum of different polynomials of different orders, so x, x2, x2, and so on like that. And in the final one, I show some example of, let's say, for example, if you have a Fourier basis, in which obviously, as you know, you have cosines and the sines that you use for constructing your, decomposing your function, your solution. Okay, so that's good. So imagine if you have to find a solution in, let's say, an nth order function space, where we have, like, nth order of polynomials, for example. That's a very massive space to look for something very tiny. So it's almost like trying to find a needle in a haystack. So one of the ideas that I explored in my PhD is how to reduce that space search problem, right? So, well, I asked the question that, okay, if you're trying to solve a physical problem in which it's, let's say, it's a hyperbolic system in which the solutions have to be transient, have to be like, waving and stuff like that, then we know that the solution has to be waving as well. Right? Like, there has to be solutions which are sinusoidal and cosines, for example. So what I do then is that instead of looking at the whole space, for example, I look at a more restricted space, which comes from an a priori idea that, okay, my solution is probably going to be inside this space. So it reduces the search space dramatically, and it helps us to use the same features of finite elements that we use classically, for example. So in this picture, what you see is that we look for the same blue dot point, but now instead of looking at in the whole space, we look into this restricted enriched space, which basically kind of guarantees to find the solution in it, and hence reducing the space in the search problem. Here is an example. So in the middle, there should be a wave which should be moving. It's moving very slow, so you may not see it moving, but trust me, it's moving very slowly. So on the left is the very fine mesh that is used generally to capture such a wave, which is basically at least 10 discrete points per length. And on the right, you see a grid, which is a very coarse grid, which can be used to capture the same wave with so much lesser degrees of freedom, like the number of points at which you have to calculate stuff. It's only because we force our solution, we force our search to looking for solutions which are wavy in nature. So there's a nice mathematical way to formulate this, but that probably is content for a separate, more chunky talk on maths. I just want to show some maths results here. Okay, there's more results. For example, in the middle diff, you can see just a pulse being captured on the same course grid. On the left, it should show an envelope of wave coming from the bottom left to all the way to the diagonally opposite end. And all of this has been captured on, for example, this very coarse mesh, which is not really possible with the classical fundamental technique. So, okay, so just to summarize some of the key features of the software. So it's compatible with Gmesh. So Gmesh is really a very widely used geometry creator. It's an open source software as well. So it's used basically to create any kind of 2D or 3D geometry that you want to use for your test, for your physical problem. For example, if you want to test how does a coffee mug, heat up, when it is inside an oven or whatever, you can create that kind of geometry using Gmesh very easily. So this code that I have basically can use whatever you create in Gmesh and translate directly to be read in this solver, and then it also calculates the outward normals to whatever boundaries you have. It's a very nice feature. You may not appreciate it fully, but the thing is, it is very useful to apply some interesting boundary conditions like one or one-type boundary conditions. So it automatically calculates whatever boundary you give to it, the outward normal to those boundary edges. Then it also gives a solution to a wide range of PDDs, as I said, the three families. Then basically it also provides explicit as well as implicit integration methods at the time. So explicit methods are basically subject to some stability conditions, and implicit methods are unconditional stable, so which means that we can really get off with a relatively larger step size in time, so it costs a bit less, and it's more stable as well. Then you've got, as I mentioned, different kind of boundary conditions that you can set up. You can also use hard and soft sources. For example, in the animation on the bottom right, you can see a source which is basically being used to generate a wave, which is a hard source in this case. Then you can also use different kind of meshing so that you don't really have to make structured meshes, which is quite an interesting bit because it makes your meshing problem quite significantly low. And then obviously you can use several different higher orders of polynomials and different kind of enrichments that you want to solve. So for example, for rate problems, you can use sines and cosines to reduce the search space. For heat problems, we can say that parabolic enrichment functions can be used to reduce the space for searching as well. So you can really try to use it with different kind of enrichments that you want, and akin to whatever problem that you see should have that kind of reduced search space. Okay, now my final slide is really about the SiMART, and I will unveil the mystery of the graph here. So basically, SiMART, as I said, is a project that I try to incorporate the power of finite element modeling with the idea of having an absolute realistic algebra. And so what it does, it got basically two parts to it. One is the finite element model, which tries to solve the problem with the classical integrational technique, or the variational principles. And there's the other part which basically looks at bookkeeping all the units. Like whenever you have a differential operator for different units, whenever you have a multiplication, how to make sure that these multiplications and divisions are consistent with the axioms of the algebra. So there are two parts to this, and so that's what we are working on. The graph here is just to show you a very simple problem that we are able to solve now using the SiMART, which is literally just a first order differential equation. It's got the analytic and the numerical solutions which match very, very closely. It's nothing big at the moment, but it's a good start. So that's what we are doing. I would highly encourage for you guys to look up Quicycle at the website, the tools that we have developed, and any contributions that you would want to have would be highly welcome as well. So thank you for your attention.
Thank you very much, Mike. Do we have any questions? I hope you solved the whole problem for us already.
Submission from me remote.
Yes.
I used to experiment with these things like discrete mesh simulations and found there was a limit at Nyquist and that kind of thing. I think you covered that in with the impulses and gradients being too strong.
Yes.
I can see this could have applications in things like audio signal processing.
Oh, yes.
Particularly approaching the Nyquist limit and optimizing time step things. And they've been really good. I can see that being applied if you could use that in parallel processing, like vector processing in these type things as well, to make it usable and practical in real time, or say physically modeling kind of thing. And there could be that's just an example application I can think of. So not really a question or a comment.
Yes.
Yeah, I like the work because it overcomes some limits that I found when I was playing around years ago.
Well, thank you very much for the comment, John. And actually, so the sampling and digital sampling and compression of data is something very interesting to me as well. And what you talked about, for example, the Nyquist criteria, how many digital points you need for compressing something, is a very interesting one. So then I had a go at this in 2018, and I thought that one of the ways to do it is something to do with making your compression, for example, agnostic of whatever technology that you have. So for example, I'll digress a little bit here from the top, but the main idea is, let's say if you have a satellite that basically takes images of whatever is out there in outer space, and you chuck the satellite into it. And 50 years later, some more smarter guy comes up and tells you the PNG is not the best compression algorithm that you have for images, right? So how do you go up there again and change the algorithm completely? So the idea was how to make an algorithm, compression algorithm, completely agnostic of any kind of futuristic developments. So one of the key features here is how do we sample? So one is to do random sampling, and then also to assume that whatever compression technique you use would utilize the idea that data would be compressible in some very niche basis, which is going to guarantee that the data is well low ranked, right? Like there are not many. Well, if you do a PCA, the principal component analysis, then there are not many components which will have a lot of energy that are required for reproducing the signal. So it's a very interesting concept, and maybe we can have a talk later. But yeah, random sampling is one of the very interesting aspects of how to have this kind of compression techniques working.
Okay, John. We look forward to how you connect this to this algebra that you were talking about. We'll look forward to that in the future.